Okay, so for today, we will look into gas turbine. In the previous chapter, or in the previous class, we have we analyzed steam turbines, which are impulse type turbine. Okay, so now we want to look into a reaction type turbine, which is gas turbine. Okay. Gas turbine industry is even larger than steam turbine industry. So gas turbine is a quite or very important type of turbine that being used in this world. Okay, some example of gas turbine that is popular or famous is turbine that been used in car engine. Okay, that is one kind of gas turbine. And gas turbine is also used in jet engine or aeroplane. Okay, so it's very important turbine. And also gas turbine also being used to generate electric in power plants. All right, so today we will look into gas turbine. Gas turbine working principle is very similar to steam turbine, but gas turbines operate at much higher speed compared to steam turbine. And instead of water vapor, the working fluid for gas turbine is gas, a different kind of gases, right? Like for turbine in car, it use the exhaust turbine, the exhaust gas coming out from the car engine itself to turn the gas turbine. And there are many type of gas turbine that use different kind of gases. All right. So gas turbine use Brayton cycle, which you have learned in thermodynamics. Brayton cycle have two type, one open cycle and the other one is closed cycle. I won't go into detail about this. And this is the TS diagram and PV diagram for Brayton cycle. If you look into this diagram, process number 1 to number 2 is called isentropic compression. It happened in a compressor. And then from process 2 from point 2 to point 3, the process is called constant pressure heat addition. And then 3 to 4 is isentropic expansion. This is happening in turbine. And 4 to 1 is constant pressure heat rejection. Okay. So we can calculate from this expression, we can calculate the heat addition using this equation, Q in equal H3 minus H2, which also equals CP3 T3 minus CPT2. And we can calculate also Q out, H4 minus H1, or CPT4 minus CPT1. I hope you still remember what these terms, the meaning of these terms. And the efficiency for Brayton cycles can be calculated using the network over the Q in. And this expression give you can calculate either using Q out, Q in, or CP, or the ratio of temperature. So whatever information it's depend on what information you have, then you can choose which equation you can use. Or Brayton cycle also can be calculated using the pressure ratio, pressure ratio is the ratio of pressure at P2 over P1. Okay, so all of these informations or all of these calculations you have already learned in thermodynamics. So now the velocity triangles for reaction turbines can be divided into two types. One is axial flow reaction turbine and one is radial flow reaction turbine. This is um, the velocity triangles for axial flow reaction turbine, and this is the velocity triangles for radial flow reaction turbine. So velocity triangles, I hope by now you have already know how to sketch velocity triangles. For axial flow, it's pretty much very similar to steam turbines, and for radial flow, it's a little bit different. So you can look into this diagram later on. I repeat a little bit. Velocity triangles. So reaction turbine we can divide into axial flow type and radial flow type. So this is the velocity triangles for axial flow reaction turbine, and this is the velocity triangles for radial flow reaction turbines. So if you as you can see here, it is pretty much similar with what we have discussed in steam turbines. Okay, especially for axial flow velocity triangles. For radial flow velocity triangles, it might be a little bit different, but you can look into this, and this is the zoom in of or redraw the velocity triangle at the inlet. Okay, at the inlet. So we redraw. You can see here W is for whirl velocity. So we use in this figure a little bit the convention of the velocity is not the same as what we have seen in steam turbines, but it doesn't matter as long as you can use any convention, you can use any symbol, but you have to declare what it is. Okay, so here W is represent the whirl velocity, U is the velocity of the blade, and VR, similar to previous one, is the relative velocity. V is the absolute velocity. Okay, and we have alpha and beta. So so this is the velocity triangle at the inlet of radial flow reaction turbine, and we have here is the velocity triangle for the outlet of a radial flow reaction turbine. Okay, you can try to sketch these velocity triangles by yourself to get more understanding. All right, and then we want to look into the energy equation. The energy equation for reaction turbines, assuming that adiabatic conditions and ignoring potential energy changes because it is small, negligible. So for a steady flow steady state, and single inlet and single outlet, the energy equation for reaction turbines is given by H1 plus V1 squared over 2 equal H2 plus V2 squared over 2 plus E. E is the enthalpy, which is given by the stagnation enthalpy. Okay, E is the energy that is given by the difference in stagnation enthalpy. Okay, H1 and H2 are the static enthalpies at the inlet and at the outlet, and H0 or H0 is the stagnation enthalpy. And from the velocity triangles, okay, using trigonometry, okay, we can get these two expressions for W1 and W2, okay, which is equal the final equation, or is U1 squared plus V1 squared minus 2U1 VU1. Okay, at the inlet, and it's very much similar at the outlet. You just change all the subscript from 1 to 2, which represent velocity at the outlet. Okay, this is just trigonometry. And then if we subtract these two equations and simplify them, we can get the energy equation in these terms, in this form. Okay, in this form. Okay, we have either this form, or this form. Okay, using these two equations, you subtract them and simplify, you will get either this form of energy equation or this form of energy equation. Okay, if we look into this energy equation, okay, the first term in this equation is actually the change in dynamic head across the rotor. Okay, its value could be considerable, as in the case of impulse turbine, which is impulse turbine. The major contribution for impulse turbine is this term, but in reaction turbine we also have other terms. Okay, wherein most of the energy change is due to the absolute kinetic energy change in the form of impulse action on the blades. So even though reaction turbine is reaction turbine, but it's also have some sort of impulse energy that is being used in the reaction turbine. So a well-designed power producing machines would have minimal exiting kinetic energy head, which we have already discussed in steam turbine. In power consuming devices, the increase in dynamic head would be the result of the power input into the rotor. If the kinetic energy head is too large, then a diffuser is attached to the end of the rotor to convert it partially into pressure. Or we can use staging to fully utilize the kinetic energy by reducing the kinetic energy or the velocity of the working fluid in stage. This is particularly meaningful in pumps and blowers, since their primary purpose is to produce pressurized fluid. However, this energy conversion occurring outside the rotor would be an energy transformation rather than a transfer. So, okay, rather than transfer the energy, it just transforms the energy. Okay, if we look into the second term in the equation, the second term in the equation represents the change in the energy of the fluid due to movement along the radius of the turbine. In a sense, it represents the centripetal effect on the fluid, and this is used in centrifugal pumps and centrifugal compressors to produce changes in pressure. Its relationship to pressure changes in the fluid can be um, demonstrated in turbine by looking at the second term in this equation. And if you look into the third term in the equation, it's actually it's not it's difficult to quantify or interpret the third term in physical interpretation. But what we can say, it is simply the change in kinetic energy due to change in relative velocity, okay, which is measured with respect to the rotor. The algebraic sum of these three terms, okay, the sum of these three terms, or the sum of the changes in these three terms or in kinetic energy give the head, the first term, and the static portion of the head depends significantly on the design and vary considerably from one type of turbine to another type. Okay, the relative proportion is described by the concept of degree of reaction. Okay, so degree of reaction is the variable that quantifies the power produced by a reaction machine. It quantified the power produced by uh, because a reaction machine is the combination of impulse power and reaction power. Okay, so the variable that quantify the power is called degree of reaction, and it is defined by the ratio of static enthalpy change across the rotor to the total or stagnation enthalpy change across the rotor, which is given by this equation. R represent the capital R is the reaction or degree of reaction. It's equal to H1 minus H2 over H01 or H01 minus H02. Okay, so H0 is the stagnation enthalpy, H is the enthalpy. Okay, so we can rewrite the reaction using the total enthalpy E, capital E, or using the U1 V U1 minus U2 V U2. Okay, combining the previous two equations that we seen in the previous slide, we can get other form of degree of reaction, okay, which is this one. Okay, you can try to derive um, the equation for degree of reaction from this form into this form using previous two equations that we have looked into previously. Okay, you can try to do the derivation later. All right, so next we want to look into the axial reaction turbine. Okay, this is the stage of axial reaction turbine, okay, which is consists of um, static and rotor. Okay. Wait a minute. Where is it? Okay, we have static or stator and rotor. Okay. The spacing along the periphery of this is called the pitch. Okay. And the pitch increases in the radial direction from the hub of the rotor to its casing. The nominal value of the pitch is at the mean radius. Okay, so this is the schematic of axial reaction turbine, and this is um, the velocity triangles at first at the stator, at the inlet of the stator, and then at the outlet of the stator going into the inlet of the rotor, and at the outlet of the rotor. So we have three velocity triangles in one stage of turbine here. Okay, if you can see, as you can see here, it consists of stator followed by a rotor. Okay, as in the previous discussion in steam turbines, the inlet to the stage is station 1. Okay, this is 1, and the outlet from the stator is 2, station 2. Okay, which is also the inlet of the rotor. Okay, point 1 is the inlet of the stator, and point 2 is the outlet of the stator and also the inlet of the rotor, and point 3 is the outlet of the rotor. For a normal stage in a multi-stage machine, the magnitude and direction of the velocity at the outlet of the rotor are the same as those at the inlet to the stator. Okay, pressure, temperature, and density naturally change from stage to stage. Okay, we have looked into that previously in the compounding of a steam turbine. Okay, so from here we can, from velocity triangles, we can calculate the work delivered by a turbine stage using this equation. So W equal U VU2 minus VU3 equal U WU2 minus WU3. What we can understand here is that VU2 is equal WU2 and VU3 is equal WU3 for axial reaction turbine. Okay. And since the stagnation enthalpy remain constant across the stator, okay, the energy equation can be simplified to this equation. Okay, you can see here there is no more stagnation enthalpy term in this energy equation. Okay, like we have looked into previous energy equation, the general energy equation for reaction turbine. But for axial reaction turbine, the stagnation enthalpy remain constant across the stator, so we can cancel out the H naught 2 minus H naught 1 in this equation. So this is what left for energy equation for axial turbine, axial reaction turbine. And the increased kinetic energy leads to a drop in the static enthalpy. So the energy equation can be written using this expression as well, using U1 minus U2 plus P1 V1 minus P2 V2, which also equal the kinetic energy change 1 over 2 V2 squared minus V1 squared. All right. So the increase in kinetic energy comes from the conversion of internal energy and from the difference in the flow work done in pushing the fluid into the out of the flow passage. Okay. This may also be written in a differential form, which is given by this equation. Okay, minus du over dl minus dpv over dl equal 1 over 2 dv2 over dl equal v dv over dl, where dl is an element of length along the flow path. Okay, this equation shows that a drop in the internal energy increases the kinetic energy of the flow, as does the net PV work term in this small section of the channel. Okay, that both terms have the same sign. Both this term have the same sign, minus, is clear for an ideal gas. For then du is equal cv dt and dpv is equal r dt. Okay, du equals cv dt and dpv equal r dt. And since internal energy drops in the flow direction, so does temperature and PV. Okay, so the ratio of these contributions is given by this expression. du over dpv equal 1 over gamma minus 1 equal 3. Okay, where gamma, the value or the numerical value of gamma is equal to 4 over 3. This is quite constant for almost all the case of reaction turbine. Okay. Okay, thus the conversion of internal energy contributes more to the increase in kinetic energy than the flow work. Okay. As the gas passes through the rotor, it is directed back toward the axis, reducing its kinetic energy. And the work delivered by the stage can be written as this equation. W equal H naught 2 minus H naught 3 equal H2 minus H3 plus 1 over 2 V2 squared minus V3 squared. Okay, now we are in the rotor. Previously we are in the stator, now we are in the rotor. With the reaction defined as the static enthalpy drop across the rotor divided by the static enthalpy drop across the stage, for positive stage reaction, H2 is greater than H3. Okay, an exception to this is an expansion at constant pressure in impulse blades. Okay, where the work can be written as U2 minus U3 plus P2V V2 P2V2 minus P3V3 plus 1 over 2 V2 squared minus V3 squared. Okay, and since each term is expected to be positive. Each contributes to the work delivered by the turbine. All right. So this is the analysis of axial turbine stage. I know it's a little bit difficult to follow because it's many of a lot of equations involved and a lot of derivation that I skip during this explanation, because I want you guys to try to do the derivation by yourself. If you don't do the derivation by yourself, it's difficult to understand where these equations come from. Okay, I just give the explanation of where this come from, where this equation come from, and you try to do the derivation by yourself. So I guess that's it for today. Stay safe. See you again in next video or our next class.